Welcome everyone to this presentation on neural networks. Today we're going to explore the fundamental building blocks of modern artificial intelligence. I'll guide you through the concepts that power everything, from image recognition to language models. By the end of this session, you'll understand how neural networks learn, why they work, and how the math behind them actually makes sense. So what exactly is a neural network? At its core, it's a computational model, inspired by how our brains process information. Think of it as a system that can recognize patterns, classify data, and make predictions, all by learning from examples rather than being explicitly programmed. The key insight is that neural networks learn automatically by adjusting internal parameters called weights. They're made of interconnected neurons that discover patterns in data through training. Let's draw the parallel between biological and artificial neurons. This analogy really helps build intuition. A biological neuron receives signals through dendrites, processes them in the cell body, and fires through the axon if the signal is strong enough. An artificial neuron does something remarkably similar. It receives numerical inputs, multiplies them by weights, sums everything up, and applies an activation function to decide its output. Look at this comparison table. Synapses become weights, firing becomes activation, and learning becomes weight adjustment. The same principles, different implementations. Neural networks come in several flavors, each designed for different types of problems. Feed-forward networks are the simplest. Data flows in one direction from input to output. Single-layer perceptrons can only solve linearly separable problems. Think of drawing a straight line to separate two classes. Multi-layer perceptrons add hidden layers, enabling them to model complex nonlinear relationships. CNNs are specialized for images. They automatically extract spatial features. RNNs handle sequential data like text or time series by maintaining memory of previous inputs. LSTMs are advanced RNNs that solve the vanishing gradient problem, enabling learning of long-term dependencies. The perceptron is where it all began, the simplest possible neural network. Frank Rosenblatt introduced it in 1958 for binary classification tasks. It maps inputs to an output by learning weights and a bias. The perceptron is foundational. Understanding it deeply will help you understand everything that comes after. We have two main types: single-layer perceptrons for simple problems, and multi-layer perceptrons for complex ones. The single-layer perceptron is beautifully simple. It takes inputs, multiplies each by a weight, sums them up, adds a bias, and passes through a step function. The step function outputs 1 if the sum exceeds a threshold, 0 otherwise. It's a binary decision. This simplicity is also its limitation. It can only solve linearly separable problems like AND and OR gates. The famous XOR problem? A single-layer perceptron cannot solve it. This limitation drove the development of multi-layer networks. Multi-layer perceptrons add hidden layers between input and output. This is where the magic happens. Data flows from input layer, through one or more hidden layers, to the output layer. Each layer transforms the data, extracting increasingly abstract features. The key difference from single-layer perceptrons: we use nonlinear activation functions like Sigmoid and ReLU. This nonlinearity allows MLPs to learn complex patterns. Training uses backpropagation. We'll cover this in detail later. It's how the network learns, by propagating errors backward through all layers. Let's understand each layer's role in the network architecture. The input layer receives raw data. Each neuron corresponds to one feature. If you're processing a 28 by 28 image, you'd have 784 input neurons. Hidden layers do the heavy lifting. They extract and transform features into higher-level representations. More layers in neurons increase model complexity, but also the risk of overfitting. The output layer produces the final result. Its format depends on your task: one neuron for binary classification, multiple for multi-class, or continuous values for regression. This comparison table highlights the key differences between single and multi-layer perceptrons. Single layer has just input and output. It's limited to step activation and can only handle linearly separable tasks. Multi-layer adds hidden layers, uses nonlinear activations, and can model complex relationships. This is what we mean by deep learning, learning through multiple layers of abstraction. Weights and biases are the learnable parameters of neural networks. They're what the network adjusts during training. Weights determine how much influence each input has on a neuron's output. A large positive weight means strong positive influence. Negative means inverse relationship. Bias shifts the activation threshold. It allows neurons to activate, even when inputs are 0. Think of it as the neuron's baseline tendency to fire. During training, we adjust both weights and biases to minimize prediction errors. This is the essence of learning. Forward propagation is how data flows through the network to produce a prediction. Starting from the input, each layer computes weighted sums, adds biases, and applies activation functions. The output of one layer becomes the input to the next. This visualization shows the flow. Notice how each connection has a weight, and each neuron applies an activation function. The final output is our prediction. Activation functions are crucial. They introduce nonlinearity into the network. Without activation functions, no matter how many layers you stack, the network would only compute linear transformations. You'd essentially have a single-layer network. Activation functions decide whether a neuron should, quote, fire based on its input. They also provide gradients needed for backpropagation. This is how the network learns. ReLU, rectified linear unit, is the most popular activation function for hidden layers today. It's simple. Output the input if positive, 0 otherwise. Mathematically, f of x equals max, 0, x. ReLU solved the vanishing gradient problem that plagued sigmoid networks. It's computationally efficient and works remarkably well in practice. The main drawback is, quote, dying ReLU. Neurons can get stuck outputting 0. Variants like leaky ReLU address this. Sigmoid squashes inputs to a range between 0 and 1, perfect for probability outputs. The S-shaped curve means extreme inputs saturate at 0 or 1, while moderate inputs produce values in between. Sigmoid was historically popular, but has fallen out of favor for hidden layers due to vanishing gradients. The derivative becomes very small for extreme inputs. Today, we mainly use sigmoid in the output layer for binary classification, where we need probability outputs. Softmax extends sigmoid to multi-class classification. It takes a vector of values and converts them to probabilities that sum to 1. Each output represents the probability of belonging to that class. If you're classifying images into 10 categories, Softmax gives you 10 probabilities that sum to 1. The soft in Softmax means it produces smooth probability distributions rather than hard one-hot outputs. Here's a practical guide for choosing activation functions. For hidden layers, use ReLU or its variants. They're fast, avoid vanishing gradients, and work well empirically. For binary classification output, use sigmoid. It gives you a probability between 0 and 1. For multi-class classification output, use Softmax. It gives you a probability distribution across all classes. Remember, activation functions introduce nonlinearity. Without them, deep networks would collapse to linear models. Now let's understand how neural networks actually learn. This is the core of everything. Learning is an iterative process of making predictions, measuring errors, and adjusting weights to reduce those errors. The diagram shows the learning loop: forward pass, error calculation, backpropagation, weight update, repeat. Let's break down each step. Here's the complete weight update process in 5 steps. Step 1. Forward propagation. Push data through the network to get predictions. Step 2. Calculate the loss. Measure how wrong our predictions are. Step 3. Compute gradients. Figure out how each weight contributed to the error. Step 4. Update weights. Adjust weights in the direction that reduces error. Step 5. Repeat for many iterations, epochs, until the network converges. This is the fundamental learning algorithm that powers all neural network training. Loss functions measure how wrong our predictions are. They're the objective we're trying to minimize. For regression tasks, we typically use mean squared error. It penalizes large errors heavily due to the squaring. For classification tasks, we use cross-entropy loss. It measures the difference between predicted probability distributions and true labels. The loss function guides training. Gradients of the loss tell us how to adjust weights. Learning rules define how we update weights based on data and errors. They're the mathematical formulas that specify weight changes. Unsupervised rules like Hebbian learning update weights based on correlations, no target labels needed. Supervised rules like Perceptron and delta rules use the error between predictions and targets. Each rule has its place. Let's examine them individually. Hebbian learning is the oldest and simplest rule. Neurons that fire together, wire together. If 2 neurons are active simultaneously, strengthen the connection between them. It's unsupervised. No target labels needed. The network learns correlations in the data. Hebbian learning is biologically plausible and forms the basis for understanding how brains might learn associations. The Perceptron learning rule is straightforward. If the prediction is wrong, adjust weights to make it right. For a misclassified positive example, increase weights for active inputs. For a misclassified negative example, decrease weights for active inputs. The beauty is its simplicity. It's guaranteed to converge for linearly separable problems. The limitation: it only works for single-layer perceptrons. The delta rule is more sophisticated. It minimizes error using gradient descent. Unlike the perceptron rule, it uses the derivative of the activation function. This enables training with continuous activations like sigmoid. The weight update is proportional to the input, the error, and the activation derivative. The delta rule forms the foundation for backpropagation. It's essentially backpropagation for a single layer. Let's compare these 3 learning rules side by side. Hebbian is unsupervised. No error signal, no target labels. It learns correlations. Perceptron is supervised, but doesn't use activation derivatives. It's limited to step functions and single layers. Delta is supervised and uses derivatives. This is what enables training deep networks with continuous activations. Delta rule plus chain rule equals backpropagation, the algorithm that made deep learning possible. Gradient descent is the optimization algorithm at the heart of neural network training. Think of the loss function as a landscape with hills and valleys. We want to find the lowest valley, the minimum loss. Gradient descent works by computing the slope, gradient, at our current position and taking a step downhill. We repeat this process, gradually descending toward better solutions. To understand gradient descent, we need to understand derivatives. A derivative measures how fast a function changes. It's the slope at any point. In neural networks, derivatives tell us how the loss changes when we change a weight. Large derivative means the loss is sensitive to that weight. We should make bigger adjustments. Small derivative means the loss barely changes. Small adjustments needed. Zero derivative means we're at a minimum or maximum. No learning happens. Let's clarify these related terms that often cause confusion. A derivative is for single variable functions, how f changes with x. A gradient is the vector of all partial derivatives. It points in the direction of steepest increase. Gradient descent uses the gradient to update parameters. We move in the opposite direction of the gradient to decrease the loss. The gradient tells us which way is uphill. We go the other way. There are several variants of gradient descent, each with trade-offs. Batch gradient descent computes gradients using the entire dataset. It's stable but slow for large datasets. Stochastic gradient descent, SGD, uses one sample at a time. It's noisy but fast, and can escape local minima. Momentum-based methods accumulate velocity from past gradients, helping speed up convergence and smooth out noise. Batch gradient descent processes all training samples before making one weight update. The gradient is averaged over the entire dataset, giving a stable estimate of the true gradient direction. Pros: stable convergence, guaranteed descent direction. Cons: slow for large datasets, requires entire dataset in memory, can get stuck in local minima. Stochastic gradient descent takes the opposite approach. Update weights after each single sample. The gradient estimate is noisy, but we make many updates quickly. Pros: fast updates, can escape local minima due to noise, works with streaming data. Cons: noisy convergence, might oscillate around the minimum. In practice, we often use mini-batch SGD, a compromise that processes small batches of samples. Momentum helps SGD converge faster and more smoothly. The idea: accumulate a velocity vector that persists across updates. Think of a ball rolling downhill. It builds up speed. Instead of just using the current gradient, we add a fraction of the previous update. This smooths out oscillations and accelerates progress in consistent directions. Most modern optimizers use some form of momentum. Backpropagation is the algorithm that made deep learning possible. It efficiently computes gradients for all weights in a multi-layer network using the chain rule. Remember, single-layer perceptrons can only learn linearly separable functions. Complex patterns require hidden layers. Backpropagation propagates error signals backward through the network, computing how each weight contributed to the error. It's gradient descent plus the chain rule applied to multi-layer networks. The chain rule is the mathematical foundation of backpropagation. If you have nested functions, like layers in a neural network, the chain rule tells you how to compute the derivative of the composition. In neural networks, the loss depends on the output, which depends on hidden layers, which depend on inputs. The chain rule lets us compute how the loss changes with respect to any weight, no matter how deep in the network. This diagram shows backpropagation visually. Forward pass: compute activations layer by layer, left to right. Backward pass: compute gradients layer by layer, right to left. At each layer, we use the chain rule to relate the gradient to the layer's inputs and weights. The gradients flow backward, hence backpropagation. Each weight gets a gradient, telling it how to change.